We're going to take a closer look at the unit cell structure in ordered crystals. So an ordered crystal is made up of a repeating pattern. That's what gives it its order. And a unit cell is the simplest, smallest cell that repeats throughout the structure. So here we have a fairly simple, just kind of lines of spheres on top of each other. So we have the center of the sphere at each corner of this cube. And so the repeating unit, the unit cell, would look like this. There are many different kinds of patterns and unit cells that you can have. Your textbook shows a table with a number of them. We are going to look at the ones where the unit cells are a cube structure, so all of these edges are the same lengths, and that they're all 90-degree angles. So that's not the case for all unit cells, but the ones that we are going to look at in this section, that is true of those. The first one we're going to look at is a simple cubic unit cell. So that is what we were just describing here, with one sphere at each corner of the cube. And some details to note about this unit cell is that it has a coordination number of 6. What this means is that each sphere is in contact with 6 neighbors. So if you look at this corner, it's in contact with the atom in back of it, the atom in front of it that's not shown because it would be blocking our view, the atom to the left, the atom to the right, the atom below, and the atom up above, which also is not shown. But that adds up to 6. It's in contact with 6 neighbors. If we look at the contents of each unit cell, this unit cell has 1 atom. So if you look at this kind of chunk of an atom here, this is 1/8 of an atom because we cut it in half, and then in half, and then in half again. So this corner piece that's showing here is 1/8. And there are 8 corners, so there's a 1/8 chunk of atom in each of the 8 corners. So altogether we have 8 pieces, and each piece is 1/8 of an atom. So we have 1 whole atom contained in this unit cell. This just looks weird because it's cut up into 8 corner pieces. In the middle of these 8 corner pieces, there's a kind of a big gap. So if you were stacking ping pong balls or softballs, they wouldn't stick together and stack like this because this softball would probably fall down into this gap. There's a big gap here, and so this one would fall to the side, and this one would fall to the side. So there's more efficient ways to stack spheres if you wanted to cram more of them into the same volume. So this volume is kind of spaced out. There's only 52% of the volume filled if you do the calculations. So there's quite a lot of empty space in this particular type of unit cell. And so of the metals that exist, only polonium has a simple cubic crystal structure. The rest of the metals in the periodic table have a more compact type of unit cell. So one of the other unit cells that we'll be looking at. All right, so let's use some of the structural information of a unit cell to figure a few things out about polonium. So we are going to figure out the radius of a polonium atom. So the spheres of polonium are packed together like this. And so they are touching along this edge of the cube. This edge of the cube has 1 radius of polonium and another radius of polonium. So the edge here is twice what the radius of a polonium atom is. So that means the radius of a polonium atom is the edge divided by 2. So it's the edge divided in half, and we're told that the edge is 3.36 times 10 to the negative 10 meters long. And if we divide that by 2, we get 1.68 times 10 to the negative 10 meters as the radius of 1 polonium atom. So for the density of polonium, we need the mass divided by the volume. The mass inside one of these unit cells is 1 atom. because we said that one atom is what's in the unit cell. So if there's one atom, then the mass is one polonium atom inside that unit cell. So let's figure out the mass of a polonium atom up here. The mass that we know of polonium from the periodic table is that it's 209 grams per mole of polonium atoms. So we know what mass a mole of polonium atoms has. And we also know that 1 mole of polonium atoms is Avogadro's number of polonium atoms. And when we cancel this mole, we come up with 3.47 times 10 to the minus 22 grams per polonium atom. So that is one way to figure out the mass of a polonium atom. Now this unit cell, which contains that mass, has a volume of the length times the width times the height. And since it's a cube, these are all the edge length. So let's put that up here. The volume of this unit cell is the edge cubed, which is 3.36 times 10 to the minus 10 meters cubed. So then we'll have the volume in cubic meters. It might be a little bit more typical to see the density being in grams per cubic centimeter. So if you like, you can convert this to centimeters first before you cube it. Otherwise, you'll have to convert cubic meters to cubic centimeters at the end. So let's go ahead and do that. There are 100 centimeters in a meter, so the edge would also be 3.36 times 10 to the negative 8 centimeters. And we can cube that. And that comes out to be 3.79 times 10 to the minus 23 cubic centimeters. So then we'll go ahead back down here and do the density. We have a mass of 3.47 times 10 to the minus 22 grams. And we have a volume of 3.79 times 10 to the minus 23 cubic centimeters. So this comes out to be a density of 9.16 grams per cubic centimeter. And this is in the right range to have the density of a metal. So metals are definitely more dense than water. They're more than 1 gram per cubic centimeter, but not too many of them are more than 10. So this is a pretty normal density to have for a metal. Another type of unit cell that we're going to look at is called a body-centered cubic. So this has 1 atom at each of the corners of this cube, like the previous one did, but there's also in the middle where this empty space is, there's another atom there as well. And that separates these spheres a little bit, so they are not touching like they were in the simple unit cell. There's a different coordination number, so this center atom is touching all 8 of these corners, but these corners are not touching each other. They're touching the, each of these corner atoms is in the same kind of position because this is a repeating unit. So if you look at the center atom, that's the easiest one to look at to tell the coordination number. So instead of being 6 like the simple cubic, the body-centered cubic has a coordination number of 8. And also you can probably tell that this space is being filled a little bit more efficiently. So instead of 52%, this is 68% of the cube's volume being filled. Also, each unit cell contains 2 atoms because it still has those 8/8, those corner pieces, those 8 corner pieces, each of which is 1/8, and plus there's an additional atom in the middle. So that is where the 2 atom calculation comes from. So we are not going to be figuring out the radius of a barium atom using this because the radius is not half of the edge. There's a little bit of a gap here and we don't know what the gap is. It's hard to tell in this particular drawing, but these are actually in contact going diagonally from maybe this back right corner to the front left bottom corner. So all the way through the cube, that's where the radii are touching. And so that's kind of a cool geometry problem. We're not going to do that. If you're interested, you can come by office hours. We can chat about that. But we're not going to figure out the radius. We'll just figure out the density, because we still can figure out the density. So this unit cell, since it's a body-centered cubic, has 2 atoms of barium in the unit cell. So the density is the mass over volume. So we need the mass of 2 barium atoms divided by the volume, which is the volume of the unit cell. So the volume is going to be the edge cubed, since we have a cube here. And the edge is 5.025 times 10 to the minus 10 meters. I'm going to go ahead and convert that to centimeters first before I cube that. So there are 100 centimeters in a meter. If I multiply it by the edge, which is just one dimension, I'll only have to do this once, and then I can cube the edge. If you cube the edge first and you get cubic meters, then you need to use this conversion factor 3 times, or you need to cube it. So I'm going to go ahead and use it first before I find the volume. So the edge is 5.025 times 10 to the negative 8 centimeters. And the volume is the edge cubed, which is 5.025 times 10 to the negative 8 centimeters cubed, which is 1.269 times 10 to the minus 22 cubic centimeters. So let's go ahead and convert 2 barium atoms into the mass. So we can convert these 2 barium atoms into how many moles there are using Avogadro's number as a conversion factor. And then the molar mass of barium is 137.33 grams per mole. So this mass of 2 barium atoms comes out to be 4.561 times 10 to the minus 22 grams. If we take that mass of the 2 barium atoms and divide it by the volume that contains them, the volume of that unit cell, 1.269 times 10 to the minus 22 cubic centimeters, and that comes out to be 3.595 grams per cubic centimeter, because I left the numbers in my calculator. If I round it to these 4 digits without leaving it in my calculator, then it is 3.594 grams per cubic centimeters, but that's pretty close. This third type of cubic unit cell is a face-centered cubic. This is the closest packed that spheres can be in this cubic structure. So another name for this type of structure is cubic closest packing. So for this setup, we have still the 1 atom in each of the corners of the cube. So we have those 8 corners with the 1/8 atom in each. And then each face has half of an atom in it. So there's an atom in the center of each face. So these 4 have 1 right in the middle, making a 5th one. And so there's 1 in each of those 6 faces of the cube. There's like an atom stuck in there. So we have, when we chop off and just have the contents of the unit cell, we have these 8 gray pieces. Each of those gray pieces is 1/8. And then each of these red pieces is a half of an atom. And we have 6 of those because we have 1 in each of the 6 faces of the cube. So altogether we have 3 plus 1. And so we have 4 atoms contained in this unit cell. And this is the most efficient packing. We have 74% of the volume filled, so that's a lot higher than the other types. And we also have each sphere in contact with more. We have 12 instead of 8 or 6 for our other structures. So if you look at this front red atom that's over here, it is in contact with these 4 gray atoms. It's also in contact with the 4 red atoms in back of it, And the next layer in front of it would have another 4 red atoms arranged like a diamond in front of it. So we have these 4 red ones, the 4 gray ones, and another 4 red ones that would be in front that are not shown, and that makes 12. So we have each sphere in contact, direct contact with 12 other spheres. So that's the closest packed that we've seen so far, and the closest possible packing for this type of unit cell. So let's see if we can do the density again with this type of unit cell. This time we have 4 atoms in each unit cell. So calculating the mass over the volume, we need the mass of 4 calcium atoms and the volume of the cube. So the mass of 4 calcium atoms, we can convert those 4 calcium atoms into a mole of calcium by dividing by Avogadro's number, and then we can convert those moles into grams by multiplying by the molar mass. And that is 2.662 times 10 to the minus 22 grams. So the volume of our cube is going to be the edge cubed, and then this is the edge in meters. This is what the edge is in centimeters. Let's go ahead and take the centimeter one. When we cube that edge, we get 1.745 times 10 to the minus 22 centimeters cubed. When we divide the mass, 2.662 times 10 to the minus 22 grams divided by 1.74 times 10 to the minus 22 centimeters cubed, we get 1.526 grams per centimeter cubed. So for this one, we are going to try to find the radius again. This is not as simple as before when the edge was 2 times the radius. This edge is more than 2 times the radius, and there's a gap in between here. We don't really know what that gap is. However, these atoms are in contact across the diagonal of the face of the cube. Let me try to blow that up over here. So here we have a drawing of these atoms in contact across the diagonal of the face of the cube. So we have a radius going from the corner to the point of contact between these 2 spheres, another radius and another radius, 2 radii going across that sphere, and then another radius going to the corner from that point of contact. So the diagonal is 4 times the radius of a calcium atom. So if we could find the diagonal and what that length is, if we divide that by 4, once we find it, we would get the radius of a calcium atom. And what we have here is a right triangle. And so we need to find the diagonal length of this right triangle, and each of the legs of the right triangle is the equivalent of the edge length. So we can actually use the Pythagorean theorem. When you have a right triangle, A, B, and C, the one leg squared and the other leg squared add up together to give the hypotenuse squared, so that diagonal line squared. In this case, A is the edge length and B is the edge length. So we get edge squared plus edge squared is the diagonal squared. And so since this is twice, we're adding the edge twice, 2 times the edge squared equals the diagonal squared. Then we can take the square root of both sides and get what the actual diagonal length is. So we've come up with the diagonal being the square root of 2 times the edge length squared. And the radius we said before was the diagonal over 4. So that is the square root of 2 times the edge squared over 4. Let's put in the number for the edge. Let's put 5.588 times 10 to the negative 10 meters. And then that is squared. And that is all over 4. And that ends up being 7.903 times 10 to the minus 10 meters over 4. which is 1.976 times 10 to the minus 10 meters. So this would be the radius of a calcium atom. So I mentioned before that we are focusing on just these 3 unit cells. There are several other types of crystal structures that you can have, and there is a drawing of them in your textbook. I just wanted to point out the diagram in your textbook that has the different types of unit cells. Again, we are focusing just on these 3, the cubic type, where the different edge lengths are all the same length and the angles are all 90 degrees. So these are the 3 that we're looking at. There are 14 types of unit cells altogether in 7 different systems. So we have ones that are more rectangle rather than square, still with right angles. We have other rectangles where none of the edges are the same length, but it's still all right angled. And then we have some that don't have all 90-degree angles, with the edges all different lengths, or with some of the edges the same. Here we have a hexagonal type of structure. Here we have one where the edges are the same, but the angles are not right angles. So these are lots of different kinds of unit cells that you can have, but again, we are looking just at these first 3. The textbook also has an illustration of the difference between cubic closest packing, which has 3 different layers, and the hexagonal closest packing, which only has 2 layers. And it has a kind of a attempt to map that face-centered cubic onto the hexagonal closest packing structure. So if you're looking down one corner of the structure, so that first corner would be one of the layers, and then the next layer would be these 3 corners around the side, and then we'd have the last layer over here kind of at the opposite corner of the cube. So it is a little bit difficult to see the cube because it's kind of tilted relative to this stack when we have the stack up and down like this. We're going to look a little bit more at closest packing systems as they relate to ionic crystal structures. So we've already mentioned the face-centered cubic unit cell that we just looked at. The face-centered cubic is the most efficient packing that we've looked at so far, and that is also called cubic closest packing. There's a similar type of structure called hexagonal closest packing, and the only difference between these 2 types is the layers of spheres that you have. In the cubic closest packing, you have 3 alternating layers like A, B, C, and then the hexagonal closest packing, you have just 2 alternating layers, A and then B and then A and then B. So there's some better diagrams of this in your textbook. Many ionic compounds form one of these closest packing systems. So unlike the metals that we looked at when we looked at the unit cells at first, for the ions, you have cations and anions that have to fit together in this ordered structure. So it's a little bit more complex than a metal where all the spheres are the same thing. So we have 2 different things. We have some anions and some cations. In general, anions are usually larger because when you gain electrons, remember, you increase the atom in size, whereas losing electrons and becoming a cation makes the atom decrease in size. I mean, there are exceptions. If you have an anion of a very, very small element and a cation of a very large element, they could be more comparable, or the cation could even be larger, but most of the time the anions are larger. And so the anions form one of these unit cell structures that we've been looking at, one of these cubic packing systems. And then the cations, since they're smaller, they can fit into the little gaps that are in between the anions. Remember that even for our most efficient packing, the cubic closest packing structure, only 74% of the volume is filled. There are some little gaps in between the spheres. So these closest packing structures have tetrahedral holes and octahedral holes. Octahedral holes are when the gaps in one layer line up exactly next to the gaps in another layer. So the two tetrahedral gaps are on top of each other and they make more of an octahedral type of a gap. So these octahedral holes are larger than the tetrahedral holes, but there are fewer of them. So the tetrahedral holes are smaller. If the cation is really small compared to the anion, like less than 40% of the size of the anion, then it can fit into the tetrahedral holes. And there are more of these tetrahedral holes. There's 2 holes per anion. So if you have 2 cations per anion, that works because there's 2 holes for the cation to fit in per anion. So that can work with a 2-to-1 ratio. If there's only a 1-to-1 ratio of cation to anion, then only half of the tetrahedral holes would get filled because there's twice as many holes as you need. The octahedral holes can fit a larger cation, so up to almost 3/4 of the size of the anion. It's still smaller than the anion, but it could be half the size, it could be 3/4 of the size. There's only one of these larger octahedral holes per anion. So if you have a 1-to-1 ratio of cation to anion, you're going to fill all of those octahedral holes. If you only need 1 cation for every 2 anions, so if the cation is +2 and the anion's only -1, and you have a 1-to-2 ratio, then only half of the octahedral holes need to get filled. So these are the kind of holes that are in a cubic closest packed or hexagonal closest packed structure. If the cation needs a larger gap, you might need to have one of the less efficient type of packing structure. Remember, the simple cubic cell was only 52% filled. So the gaps in a simple cubic cell are a lot larger and they can accommodate a larger cation. So this can fit a cation up to the same size as the anion. So 3/4 of the size up to equal in size with the anion can fit into these larger cubic holes. And there's only one of them per anion in the structure. So it works fine with a 1-to-1 ratio. If it's half filled, then you only get 1 cation for every 2 anions. So let's see if we can reason out the type of holes that would be filled from a formula, or the formula from the type of holes that are filled. All right, we are told that manganese and sulfur are forming an ionic compound together. So sulfur is the anion, and manganese is the cation. We have a metal and a nonmetal. We have a cation and an anion. So manganese is in half of the tetrahedral holes. So what this is saying is that for every 2 tetrahedral holes, we have 1 of them filled. So 1 out of 2 is filled, 1/2. And so for every 2 holes, 1 of those holes is filled with a manganese atom. Also, from our knowledge of the closest packing structure, we know that a closest packing structure has 2 tetrahedral holes per anion. So for every anion, there are 2 tetrahedral holes. Our anion is sulfur, so I said that we have 1 sulfur. This isn't a 5, it's a S. 1 sulfur anion. There's 2 tetrahedral holes for every 1 sulfur anion. So if these 2 statements are both true, that we have 1 manganese for every 2 tetrahedral holes, and we have 1 sulfur for every 2 tetrahedral holes, this means that we have 1 manganese ion for every 1 sulfur ion. And so the formula would be MnS. So this would be a manganese 2 sulfide structure. All right, this next structure, we have aluminum in 2/3 of the octahedral holes. So for every 3 octahedral holes, 2/3 of them, or 2 of them, 2 out of every 3 holes, are filled with aluminum ions. Then from the structure, a closest packing structure has 1 octahedral hole per every anion. So every 1 oxygen anion has 1 octahedral hole. So let's go ahead and multiply this by 3 so that we can match with what this relationship is. So 3 octahedral holes would correspond to 3 oxide anions. If we combine these two statements, the first and the third, then we get the relationship that there are 2 aluminum ions for every 3 oxygen ions. And then the formula would be Al2O3, which is a formula we recognize from before. This is the correct formula for aluminum oxide. Okay, so again we have a compound with octahedral holes. And a structure with octahedral holes has 1 octahedral hole for every 1 anion. And then according to the formula, we have 1 titanium ion for every 2 oxide anions. So let's go ahead and double this first statement so that the oxygen anions can match. So there's 2 octahedral holes for every 2 oxide anions, and there's 1 titanium ion for every 2 oxide anions. So reasoning this out logically, that means there's 1 titanium ion for every 2 octahedral holes. So for every 2 holes, 1 of them is filled with the titanium ion. So that means that 1/2 of the octahedral holes have titanium. So 1/2 of the octahedral holes of this compound are filled. 1 cation in every 2 holes. So here we have an example of a simple cubic cell that has cubic holes, because the cation is relatively large. Fluorine is such a small anion that calcium is a little bit large. And so that structure has a cubic hole for every 1 anion. And then we are talking about half the cubic holes being filled. So for every 2 cubic holes, 1 of them is filled with a calcium ion. So there's 1 ion for every 2 holes. That makes them half filled. So let's go ahead and double this so we have something that corresponds to 2 cubic holes for this relationship as well. So now we see for every 2 cubic holes we have 2 fluoride anions, and for every 2 cubic holes we have 1 calcium cation. So that means we have 1 calcium ion for every 2 fluoride ions, which would make the formula CaF2 for calcium fluoride. And this makes sense knowing what we learned before, that fluorine is a -1, the fluoride ion. So we would need 2 of the fluoride ions to balance the 1 calcium. So yes, this makes sense as the formula. And it also means that half the cubic holes are filled. Okay, so this is another problem where we have the formula. So we have 1 zinc ion for every 1 sulfur ion. And then the zinc is in some tetrahedral holes. We want to know how many. So for every 1 anion, we have 2 tetrahedral holes. That's how the closest packing structure works. So if there's 2 tetrahedral holes for every sulfide anion, and there's 1 zinc ion for every sulfide anion, then that means there's 1 zinc cation for every 2 tetrahedral holes. So for every 2 holes, one of them is occupied. 1 out of 2, or 1/2, the holes are filled. So this type of structure has 1/2 of the tetrahedral holes filled. So we were talking before about the length of the edge of a unit cell and how long that unit cell is. And you might wonder, how do we actually know the spacing of the unit cell? We can't hold a ruler up to it. That's definitely not going to work. So one of the things that we can do is use X-ray radiation. The wavelengths of these radiation are on the right level, the right size, to be able to diffract when hitting these layers of atoms. So if you are aiming X-rays at the surface of some crystals at different angles, you will find an angle where the X-ray that hits one layer is in phase with the X-ray that hits the next layer down. And that will cause the reflected wave to be brighter because it's constructive interference. These waves add and they don't cancel each other out. So you might notice that this particular beam has a longer path than this one, but it's longer by an integer number of the wavelength. And so that's what makes these waves in phase. In order for these to be in phase and this constructive interference to happen, then a certain multiple of the wavelength has to equal 2 times this distance between the layers times the sine of theta. So it's kind of complicated trigonometry to reason that out, but once you have this Bragg formula and the proper amount of information, you can actually figure things out fairly easily. So for both of these problems, we are figuring out the space between the crystal planes. So that is this red line here. How far apart are these layers? That's what we're looking for. And in the equation, that is this variable d. So we're looking for d. The spacing between the crystal planes is d. And this pattern has first order diffraction. So when this n in front of the wavelength is 1, it's a 1 multiple of the wavelength. And the angle theta is 16.21 degrees. So if we solve this equation for d, we get n times lambda over 2 times the sine of angle theta. So plugging in these numbers, n is 1, the wavelength of the X-ray is 0.2287 nanometers, and then we have 2 times the sine of an angle with 16.21 degrees. So if you have a scientific calculator, just make sure it's set to degrees. That's the most common problem that I see. If it's set to radians or gradians, this is not going to give the right answer. But 16.21 degrees, if you take the sine of that and then double it, it should be 0.5583. And so the spacing is calculated to be 0.4096 nanometers in between those layers in the crystal. So we're looking for the second kind of thing in the next problem. We have the same equation, the same setup. This time the n is 2. This is second order diffraction. So we have 2. The wavelength is 0.1455 nanometers. And then we have 2 times the sine of the 20.11 degree angle theta. And so that gives us 0.2910 nanometers over 0.6876, which gives a spacing of 0.4232 nanometers.